All right, we're off again. It's Friday, and here's the day's agenda. We'll start off by going through some exercises from last time, and once that's done, we'll move on to the topics listed here. We'll talk about the complex logarithmic function, the complex exponential function, and the fact that it's periodic. And next, we'll dive into an introduction to complex algebra, meaning we're going to review some vector calculations from your math at the B and A levels. So we'll touch on the concept of vectors, addition and subtraction, scaling and unit vectors, direction and normal vectors, dot and cross product, and finally straight lines. But let's jump right into solving a couple of problems from last time. And ask, you had one called algebra number 5, and it goes like this. Yes. -2, isn't that what I had written? But in this one, you're supposed to recognize it as the square of a binomial. And if you calculate it, it gives you the square of the first term, where both factors are squared. So that gives 4a squared. Then I take the second term squared, which gives +1. And then I need to square that term, which in total gives 4a. So the double product yields 4a, which gives us that. And that's identical to the denominator, which is also 4a squared plus 4a plus 1. So they cancel each other out. The entire numerator cancels with the entire denominator. And it doesn't equal 0, but equals 1, because the fractions numerator and denominator should always make 1. So there is really just 1 minus 2 left here, and not 1 minus 2.
So that's obviously -1. So that means no matter what test you have,
whatever the value I place for r here, here, and here, when I work all this out, it always equals -1. So it was just a -1 in disguise. Any other requests? No peeping nails? Is that why there are no questions? They haven't really been recognized as questions. What about the integrals? Can you make sense of them? Shall we do a couple? Do you have a preference, CERN, for one of them?
Yeah, you shouldn't take one of those. Just try to name one for me.
Yes, so this is what I need to integrate with respect to x. So what you need to get used to when looking at these integrals is to scan them for family. We look and ask, is there a family between two functions here? Yes, there is. Is 2x differentiated, which yields 2? So you can think of this as the inner function, g of x, and the total thing can then be thought of as g prime of x, and Cn can be considered as a function f that operates on 2x, or in other words, operates on g. And then there's the integral sign and a dx, and if an integral has this mathematical structure right here, then we can use integration by substitution, which simply means integrating by switching out the variable.
So I'm putting 2 times to the heated
in a
T.
tag box.
So I differentiate T with respect to X.
This means that what's coming up next is just how one always does when making a substitution. So I say dt dx, then I work out what that gives us. It gives 2, because the derivative of 2x is 2. So I multiply by dx on the other side and isolate dt. dt is the same as 2 times dx. And then my thought process is complete, because I can see that 2 times dx was exactly what was written here. So that must correspond to dt. So this actually represents dt. And this last part here, that's what I named calt C. So it is actually g of x that you add time to. So that means this integral, if we write it out again, actually becomes the integral of the sine of something. And that's something with t.
Walking is something, and that's part of it.
So my integral has now become much simpler, because now I just need to find a function that, when differentiated with respect to t, becomes sinus to t.
And that must be x-nus t.
And then add k. So here's the answer. These are all the antiderivatives of sinus t, but some might not like that it says t, because the original question was formulated with x. So you just substitute x for t.
T bar, which is 2 times.
And there's the answer, so we can use it. Any questions on that?
Does that make sense now?
And sure
So
enough, there was another one
Didn't
I
I
had.
write down a different number there? If I remember correctly. Just teasing a little.
So I have integrated a cosinus. Yes. So I've been a bit
And I
sloppy
don't
there
have to do that.
then you'll
Because
get
I
the
have
hang
a
of it.
family like mine.
because differentiating x squared doesn't give you 3x. Differentiating x squared gives 2x. But 3x is similar enough to 2x that the substitution still works.
And that means at most there can be a constant one needs to multiply by.
To fix the problem. There can't be anything wrong with x, but it's okay to have something wrong with a constant. So if I just make my substitution, I'll call it g in here. So this becomes g prime, and this out here, that's f. So I have the structure again where f acts on g, and then there's a multiplication with g differentiated. So I'm setting t to be x squared. And now we differentiate t with respect to x, and that gives 2x dx. So I can see that if I multiply by dx on the other side, I have something that looks like 3x dx, though it's not exactly 3x dx. So I just multiply by dx over there and consider this as a fraction. Then dt becomes 2x dx. And then I think, I don't have a 2 here. I have a 3, so this doesn't become the number 2. And then I create the number 3 by multiplying by 3 as well. So I multiply by 3 halves on both sides. So if I multiply by 3 halves, then it says 3 halves times dt equals 3x dx. Because if you multiply 3 halves by 2, you just get 3. So you have that. And then the thought process is essentially complete, because what I now see is that what you actually have is the integral of. Now let's focus on something. And that is something. It amounts to something.
And what it says here apparently is 3.5 dt.
And that can be resolved because the 1.5 is a constant. So I need to move it out front all the way
Just
to the left.
then.
So I'll just set it to 3.5 without degradation.
And I think, what's the antiderivative of cosine? Well, it's sine.
So sine took t. And what was t? It wasn't cyan. And then suddenly it boiled.
And there we have it. I'm done. Here's the answer. These are all the antiderivative functions for this integrand. And if you feel like it, you can certainly give it a try. 3.5. What happens to it if I try to differentiate it down here? It remains unchanged. The derivative of sine gives cosine to the same interior as before. That's correct. The interior itself, when differentiated, yields 2x. But multiplying 2x by 3.5 gives us 3x. So it checks out. Are there any other experiences we should look at? Otherwise, I highly recommend that everyone make sure to complete all those assignments from last time, if you haven't already. And if you're unsure, just go over some of the video clips again to become proficient at algebra.
And integrals and calculus. So it must be the board I want cut now. And now I'm going to cut it out. Now we're moving on to take 2. Well, back to the complex numbers.
We need to get those done today. And
One of the latest things we talked about with complex numbers was the complex exponential function.
so that's the headline right now, the complex exponential function.
So I'll just take this point before I move on to that one up there.
What we mean by this is what happens if you take a complex number.
Z called explosive.
So it's a complex number written in rectangular form. What happens if you take such a complex number and use it as an exponent for another number, like this?
What's the result? Whatever it is, I'll give W a quick call.
So this is my input to the function, and this is my output from the function. Here's the thing about the output. And that's the thing about input. So you have to imagine that, Z, it's a known quantity.
And what we're looking to find is W.
We need to find W. And let's say that the W we need to find, we're trying to locate it in polar form. Using Euler's notation, it looks like this. So if we need to find W, who is it that I need to find? R and phi. If I know R and phi, then I know everything there is to know about W. What it now tells us about W? Well, it tells us how far W is from the origin. That's what we call the modulus of W. So big R means what is the modulus of you, dear W? So that means how far away are you from R? So if I were to make a little drawing, let's say W is right here. So that number is how far it is from here, and that's how far out it is. And the other thing I need to know if I'm to understand everything about W is the angle phi. And phi is right here, because that's the angle of rotation from the positive part of the real axis. From here up to the line that connects the origin with the complex number W, that angle, that's fine. And what we saw to find W is simply to take that expression for Z right here and slam it into Z's place over there. Then you find it. So this is just pure repetition from last time, what I'm doing here. So what does E and the Z's become?
Yeah, it turns out to be e to the power of x plus I times y.
And we can break that down as e to the power of x times to the power of I times y, due to a rule of exponents that states that two powers multiplied together with the same base is the same as that base raised to the sum of the exponents. We learned this in algebra some time ago. We know this is supposed to give us W because it's stated here that e to the power of z should yield W. And we want to know what W is. So here I can write W. With Euler's notation, and by just comparing this complex number with that complex number, I can draw a conclusion now. If one complex number is to be the same as another complex number, then they must have the same modulus, and they must have the same argument to nearly a whole multiple of the angle.
So that means what's written here in front needs to be answered.
Just with what's already given here. You probably remember that everything in front of Euler's number in Euler's notation is the modulus. So this right here is the modulus of this complex number. And this is the modulus of that complex number. This means we derive the equation written here. It leads to two equations.
And one thing is that the x's have to give an r.
It's got to be. So that equation can't be true, can it?
These are complex numbers. They can't be equal unless they're equidistant when plotted. And this equation can be solved completely. You can actually find x just by taking the good old-fashioned natural logarithm of r. So there's nothing complex about this equation. Everything is real in this equation.
E raised to a real number should yield a positive real number.
So now we're halfway there. Now we've found x.
And that's what we will need to find. Wait, stop. I'm in the middle of the most complex logarithm. Sorry, I have to stop here. Now I've found r.
I accidentally mixed up the story with what I was about to tell you in a moment.
So the story belongs to the future. Sorry. What you gain by getting up and thinking ahead, you shouldn't do that. You should just be here and right now. And another thing we can say is that the weight y should equal the file.
So I has to equal phi and close to a whole number of full rotations.
And that's what mathematicians call almost a whole multiple of 2 pi, or in plain Danish, just shy of any whole number of full circles, because 2 pi is one full circle. And a whole number is written like this. P must be an integer. So it should belong to the set Z, which stands for the integers. And this set Z, let me just repeat that for you. Z is this set of numbers.
So 0 plus or minus 1, plus or minus 2, plus or minus 3, and so on into infinity.
And that means when P belongs to Z, you can either, if P is the positive numbers, go this way around, or you go that way around. And if it's the negative numbers, then you go that way around.
But in both cases, it turns into something completely different.
At a T med angielski vinder, jeg gør hvad jeg også det også som svar på det. I det sanger sådan ismo som
So here we can also draw the line.
And that's how you use the complex exponential function.
This is how the two conclusions go.
And we're actually pouring out an example here. Let's say we need to find c such that a to the power of z is 0. That gives us 3 Euler's number raised to the power of a times 3/4 p.
No, it's me now. I just keep thinking beforehand.
I need an example where I have to find double consonants. So I have to say E.
Find themselves uplifted by something enormous. It should give
something unknown. So over there, it's unknown.
So it's unknown. It's known.
So I come up with like 2 plus 3, for example.
So if z is 2 plus 3i, what does a to the power of z become? That's the question one asks oneself when dealing with a complex exponential
You
function.
feel good about it.
So what does e to the z turn out to be? So what then does e to the c equal?
Yes. It has to be the E
2
experience.
plus 3i.
We can rewrite 2e raised to the I times 2 times e raised to the I times 3. And from this we can now see that's what it is right there. It must correspond to R.
And that must correspond to Fig.
So now we've found W. We knew Z, and we had to find W. In just a moment, we're going to do exactly the opposite. That's why my brain has been fogging up and stalling. So the conclusion is that W is located at a distance squared of Euler's number away from Orgeco. That's one conclusion.
And the angle, the argument for W,
Which is enemy, that will be 3. And if I didn't specify otherwise, then we were dealing with radians. If I put a degree symbol here, it would mean degrees. But since I didn't, it's radians. And with that, we're done. That was the example.
How to use Euler's complex exponential function.
have you commented?
So when we write AARG, it means argument, which is just another way of talking about one of the angles. If it says 2 Tashriks, just put in 3 rad. That's exactly right. Right question. So what did I write down? The E in the sentences is periodic. That's what I needed to share. This was just a review. And what does it mean for something to be periodic? Well, it means the following. If you have something that's periodic and you graph it, it means that the graph repeats itself after
There's a certain period. So now I have a graph that looks like this.
and now it looks like this again. Obviously, I'm faced with a challenge bar. That was an attempt to draw the same thing that was there before, right?
So we're simply
Distance
ready.
repeats itself after a while, so we call it periodic. And the distance that repeats itself, that's what we call the period. So this right here is the period. An example of a periodic function is sine or cosine. They repeat themselves, and the period is 2pi. Because when I draw a sine curve, the sine curve starts as a periodic function. A sine curve starts a periodic function.
Because the sine of 0 is 0.
Then it goes and comes 1, falls down, turns back to 0, falls even further, goes negative 1, and then goes back up to 1.
And then I'll just repeat that otherwise.
Here comes the same image again. That image is recurring periodically like that.
And how long does
Now
that
I have
take?
to wait before it repeats itself for such a long time. That's quite nice.
Hey again, good to meet you.
2p of sine.
And it's 2p when it's correct.
So I'll repeat the whole story again with the xy coordinates for the point on the unit circle. And what I'd like to show you is that Euler's exponential function is periodic. And the period isn't 2 pi, the period is 2 pi I.
2 pi, because we also need to start with the little mark of unities.
So to show you, let's move on to the next board.
And it's also pretty cool to be able to say right up to the exam, just in case you get lucky and draw question 3 on complex numbers. A mathematical presentation almost always starts with a proposition, which mathematicians call a theorem, and then one proves the claim behind it.
So now
I'll
I'm
write
setting it
a
up,
theorem.
and then I'll prove it.
Here comes a sentence about the complex exponential function. The sentence says, the function f of z equals e to the ith power of z equals w
Is periodic with a period of 2 seconds.
It's periodic, meaning it repeats its level of
Gender
function.
norms after a certain
Are
forehead.
you out to? And the specific period is, the claim states
2 times p times the imaginary unit a.
and that is such a purely math nerdy statement, we're probably never going to use it for anything. But it teaches us to think about these things in case we might need it. So here comes the proof. Let's just try once and see what you get if you say e to the power of I times theta, and then you add 2 pi I to it. So first one thinks, what does e to the power of I times s yield? And it yields e to the power of I times s. Then one wonders, what can we end up with if I add 2 pi I to it? And it turns out that you get the same as e to the power of I times s.
Let's give it a shot. What was c again? C was x plus I.
So we can write z here. Here it is with x plus I times y.
It's a complex number after all.
So I'm putting that up for sale over there.
So it says e to the power of x plus e times I plus 2 times pi times I.
This is just getting into disguise. That's what it says there.
And we can expand on that. We can simply write it like the examples.
And then I can place I outside the parentheses because I is multiplied there and there. So it should be I plus 2 pi. But this is, of course, a complex sale. And this complex number, how far away was it from yesterday? The EGX, it's that far away. And what's the angle of this complex number? Y plus a full rotation. Y plus a full rotation lands us right back where it points, because y is the angle. So therefore, this is the same complex number as e to the power of z. So this is the same complex number as this one. And the next difference is a full rotation, which brings us back to the same point in the complex plane. So it's the same complex number. And this I recognize as e to the power of z. And that proves it.
A to the power of ez plus 2 pi is the same as what e to the power of iz does.
Just like that, periodically.
It then repeats itself with a period of 2p.
All right, let's talk a bit about the complex logarithm function. Meaning, now I'm going to ask you to keep your tongue straight in your mouth. I have to remind myself of that too. It's tricky enough. But now we're moving on to a new section about the complex logarithmic function. This time we're going to do the exact opposite of what we've just done. So now we introduce the complex logarithm. And make sure to spread it out nicely so I don't end up stumbling around in it. What's going on now?
And logarithms.
Well, yes, that was an exponent finder.
So if we have something that looks like this, can you tell me what 2 to the power should be?
Pledge to give one's word.
So thankfully we can figure it out because 2 times 2 is 4. And when you multiply by 2 again, I slowly get to 8. So if you put 3 up there, then the money adds up. See what I mean? 2 to the third
It's
power.
8.
So this equation, it has been solved.
X6 should be 3.
And now I've found an exposure. And now I found exposure. And because I found
How have I
exposure.
used a logarithm without saying it? Since logarithm means exponent finder.
And what I've actually done is that I've taken
The binary logarithm of 8. And you write it like this.
Log 2.
To the year.
what is log base 2 of 8? It's 3. Why is it 3?
Because 2 to the power of 3 equals 8. And log means, can't you just find the exponent?
If I'm reading in Danish, it says, can you find the exponent that works on the number 2 to get to 8?
And the answer is 3. 2 times 2 times 2. That's 8.
Another example could be to ask, what power should 10 be raised to? Now we have a new base number in order to express 10,000. So there's also a new right side.
And again, we can figure it out because
The exponential function that uses 10 as a base is really easy because it fits our decimal system. So you just count the zeros.
That was tough.
That's the beauty of the decimal system. Here, I can find the exponent that acts on 10 to make 10,000, and that exponent is 4 because there are 4 zeros. So this is the answer. But in reality, I used a logarithm. And which logarithm did I use? I used the common logarithm, and then I applied it to the number 10,000. So it looks like this. This is the same as the common logarithm taken to 10,000. So what does it say here in Danish? It says, what should 10 be raised to? So that 10 becomes, when it's raised appropriately, 10,000. But 10,000 can be written as 10 to the 4th power, right? So now I'll read the question again, and it's ridiculously easy. What does 10 need to be raised to for 10 to have been raised to what I'm pointing at now? The answer, of course, is what you're pointing at.
So that makes 4.
So now we're ready for the complex logarithm because we've reviewed what a logarithm is. Something nice and easy. It's something that's easy to relate to. So now that we're convinced it's easy, we're ready to dive into the topic that includes the word complex that we're about to discuss. Okay, so let's see what we might come up with to ask about.
what should Euler's number be raised to?
And that results in some kind of huge complex number. So now you've got to imagine that this detail is what you know, and what you don't know, that's the exponent. And when you're facing the monthly exam, and just like I sometimes doubt, you doubt. How can you ensure that you can reason your way to it when the logarithm finds the exponent? So here is the exponent I need to find. So that must be the one I know. So if you're working through the section titled Complex Logarithm, we know the exponent I need to find. Now, I need to figure out that one up there. And that one is known.
So we write here set.
Acknowledged.
However, W must be found.
Over. Let's say that the set that is known.
It's written in lizard script like this.
So I know C. It's not the one I need to find, but I need to find W and W. I write that down. What can you leave out? That's the cleverest part, you see, when you have to explain complex logarithms. Now I take that expression for Z and put it on the Z spot, and I take that expression for W and put it on the W spot, and then I get what's written here now. I get Euler's number raised to the power of x plus iy. We have to find Z, but Z is r times e raised to the power of a. And you have to keep thinking, what is it that I need to find? And what is it that I already know? Because it's all in symbols when you stand for your exams and do derivations.
So once more, what was it I need to find? It's x and it's y that I need to find. Because I'm looking for the dovetail.
I need to find the egg hunt.
So I can do that clever rewriting I've seen before, where I just say e to the power of x times e to the power of y.
So I'm rephrasing from that to that.
And on the right side, I'll just copy paste myself. And then you'll argue, as we usually do, two complex numbers can only be equal if they have the same modulus and the same argument. practically an integer multiple of 2 pi. This means that e to the power of x must yield r, and that means y has to give phi plus 2 pi. So this gives rise to two equations. Equation 1, e equals mc squared.
Yeah, that's a mess.
Am I finished
Hello,
here?
hello.
I was done before when it was about the complex exponential function, but now I need to find x. So I'm not finished until I've isolated x, and that's what I was doing before. Because my brain just mixed up the two stories. And if I need to find x here, I have to look for an exponent, but now it's a real number. So now I can use the good old real logarithm with base e, and that's called ln. So x can be found as the natural logarithm of r. Do I risk that the value of Stora is a number I can't take the logarithm of? No, because you can take the logarithm of any number that's positive. Modulus r is a magnitude, so it's a distance, and a distance can't be negative. Could it possibly be 0? Is that only theoretically okay? If that was 0, then it would require that c be 0.
So
Equation.
this one cannot
Solve
take the
the-
0 position.
So let's write that down here.
Sit
It's
down.
definitely not 0. So then I can't find the natural logarithm of the modulus, because then the modulus is 0. But every other complex number is 0.
Can be put back in its place, and then I can find the day shift.
And the second equation states that y must be the same angle as phi. That's equation 2. Y should be the same angle as phi, or plus or minus, a whole number of complete revolutions. Because the full circuit points to the same place. So now I've found x is right here. I've also found y is right here. So what have I found then? I've found the logarithm. I found the logarithm of z because I found w. So w, that was what I needed to find. People say that's the logarithm of z. And how many answers are there to that question? Finally, many. Specifically, one answer for each chosen value of p. There's only one correct answer for x, right? The real part is simple. It should be the natural logarithm of r. But the imaginary part, what I'm searching for, that is for w. There are many possibilities to disagree on. So there are infinitely many complex logarithms. A logarithm for every chosen value of p. So how do we write this? Well, what was w again? It was x plus I times y. So that's what I'll begin with. But I did find x was the natural logarithm of r. So this can be written as the natural logarithm of r.
And I've also found y. It's phi plus p times 2p.
And I've got to remember to multiply it by the I mark close unit. So here they all stand. Here are all the infinitely many complex logarithms. There is one for every complex number, as long as the number is not 0. So here they all are. And there's one of them that's particularly appealing. It's the one where this angle here becomes a principal argument. That one is called the principal complex logarithm. I'll write that on the next blackboard. But before I erase this, let me just go through it once more, uninterrupted, so you can hear the whole explanation without taking notes, because this is not the simplest concept to grasp when dealing with complex numbers. You'll need to work through it a few times on your own.
The headline is the complex logarithm. What does that mean?
This means that you can find an exponent, even if it's complex, because a logarithm is like an exponent finder. So let's go through a couple of examples. If we need to find the exponent that works on 2 to get 8, then the answer is 3. If you ask the converter, then it's the principal logarithm to the 8, done. If you ask, I need to find the exponent that works with 10 to give 10,000, then the answer is 4, because 10 raised to the 4th power is 10,000. And if you're asking the calculator, you'd look for the logarithm of 10,000. End of story.
But now the complexity increases a bit because now I'm asking,
You get that you know z, which is a known complex number, and it can be anything, it just must not be 0. Can you then find the exponent that works on Euler's number to yield z? If you can do that, then it makes sense to call it the complex logarithm because it's a finder of a complex exponent. Are you all following so far? So we're looking for the W that, when used as the exponent on Euler's number, gives us set. We assume Z is known. We just need to find W. We represent W as x plus iy because that turns out to be the wisest approach. And we express the known Z in the form r times E to the power of E phi using Euler's notation because it turns out to be the smartest way. Some have tried other methods, but they don't work as easily as this one. Well, that I can just take Z
And then you're speechless.
and write here on the right side with cursive, and I can take a W, which is unknown,
Question.
and substitute it for Z's place or for W's place right there. Then I get this line, and that line quickly becomes this line by using a simple rule of calculation. And this line indeed cuts through that and that line because it implies that this one has to equal that one, and this angle has to be the same as that one, except for an integer number of rotations.
And if the exceptions are to
The big
apply,
ones
then
are-
of course we can X.
So I just need to use the exponent finder that finds x in it.
And that's a real exponent finder.
So that's the good old-fashioned natural logarithm. And the weight should be phi plus p times pi, where p is an integer. By the way, when you write L and GZ, that's mathematicians' way of indicating that it's a complex logarithm. So this is not a common logarithm. It's a complex logarithm, and you can tell because there's a big Z. If it had an x, it would be a common logarithm, but if it's a Z, it's the complex one. And there's no doubt about it. When you look further and think that it's complex, you can tell right away because it involves I. So there are infinitely many answers to that question. There are infinitely many different exponents you can plug in there that yield Z, and all of them are listed here, one for each chosen value of P.
Were you in on that? That's the story.
And the last part of the story is that if the principal value of the argument lies between minus pi and pi, then we call it the principal value. It also means one that I really like. And here are the others that I also like, but just not quite as much. Okay, so that was the story. Let's jot it down with the principal over here before I wipe that off. So this one, write with a capital L for principal, and then the end, ln with a capital L. That's the complex logarithm, and it's the principal one.
So what's it all about? It's all about the line number.
The same to you.
Pretty wild.
And look, I've dropped that p to 2 pi thing. I'm just taking one of them. And then I say, if that angle that falls in the interval was from negative pi to positive pi, so this is called the principal logarithm. That's it. It is called the principal complex. Well, I don't know anymore.
It is what it is.
So let's just work through an example. So let's try to work through an example. It might make it a bit easier to grasp. Here comes an example. So we need to fix this wire. E, lift in W. Should I assign some number C and I need to know it? So let's call it 10 times Euler's number raised to the power of A times 1.5 B. What am I looking for here? Well, there's only one thing in the equation that I don't know. That's Euler's number, a known quantity. And this is a known complex number. So the only thing I don't know is the exponent. And to find an exponent, you have to use logarithms, no matter how you look at it. And if it's a complex number you're looking for, then you need to use the complex logarithm. To solve this, I'll just use the conclusion written right here. Bam. You can forget the whole derivation. That's just something you do to show off your chops for an academic exam. Now, I simply use the conclusion. Equals the complex logarithm of z, which means the complex logarithm of that thing over there.
EII before.
Half. And what does that give us? So let's just take a look over here.
It delivers expert
Current
results.
times 1/4. So that gives x plus I. U.
What is x?
X are the lengths.
So it's the natural common logarithm, the real one, raised to r, which is just plus the imaginary unit times and a 6. The angle is pi, but it's already there. 3/2 pi. And then plus an integer times 2 pi. All the answers are listed right there. Here are also logarithms for that number. All the complex logarithms for that number are written right here. Good evening. So we finished with the complex number. So I'm not sure what we'll use the rest of the semester for. Oh yes, there are also some other topics, but that was all about complex numbers, which are on our syllabus. And how do you learn that? Because you might be sitting there thinking, can I remember all this? No, you probably can't, but you'll learn it by practicing in pairs at a blackboard. So if you haven't started on this yet, it would be smart to get going. Every now and then, just stay here and use half a sim. One afternoon, try standing at a board and attempt to go through some of it. How much time did you spend studying for the exam? Mikkel, do you remember?
And move to new places.
A whole weekend.
And more.
In 2 days.
8 hours, 2 days. It's quite efficient. I think you should expect that it will take about 3 days on average. Maybe some will need 4, and maybe a few might only need 2. If you can do it in 2 days, that means you've done a lot during the semester, that you were here, listened, and understood most of it. So I would probably recommend that you try to set aside 3 days to study for the math exam, 8 to 10 hours a day. Just eat pizza, drink cola, stand at a blackboard, and practice. And you can learn it, that's for sure, 100%. I've never ever seen anyone who, if they've spent 3 days studying for an exam, turn out to be a failure. I can say that with certainty. So you won't fail. If you practice enough, you'll be well prepared, at least enough to pass.
Haha, that's local hero stuff delivering to the school. Yes.
But not everyone is keen on remembering it for a long time. So if you can just remember it until the exam, then I'm happy. Among the engineers I work with, those who haven't touched grammar since becoming engineers, very few of them remember anything at all. But if you learn how to study for the exam, you'll at least remember it for a couple of weeks. And the cool thing is, and that's why you study engineering, now if you need it, you can relearn it super quickly. And that's the most important part of becoming an engineer. You get much better at learning. You learn and learn, you get better. A lot of what you learn, you'll never need. But what you get out of it is becoming good at taking in something new. Well, the undeniable truth is that much of what we teach you, you'll never actually need. But you're going to need to learn and keep learning new things.
There's only cheating in the exam, John.
Those were the complex numbers.
I'm thinking we take a quick break, and then I can pretend I'm rushing off to an exam on one of those topics in complex numbers, so you guys can see how one could do it. Let's just take a break. Sure, and if you wouldn't mind feigning question 3 and reading it out loud for me, I'll start a timer, so I don't take too long.
Thank you for tonight.
What's the question? Yes, that's what we'll start with. Why were complex numbers invented? I imagine I am in an exam and need to talk a bit about it. Well, it's because if you have an equation like this, 1x squared equals minus 25. There are no real numbers that can solve the equation. There are no real numbers that when squared produce a negative number. This issue does arise. It does. And it's not that it has no real world significance. It does. There are simply no real numbers that can solve it. That's why we've invented complex numbers. And as soon as you introduce complex numbers, you can actually solve this equation by saying that it results in either plus or minus 5i. Those two numbers solve that equation. Because if you take 5i squared, what does that give you? 5i squared is 25, and I squared is minus 1. And minus 1 times 25 is minus 25. So we see that the number 5i squared equals minus 25, and therefore it solves this equation. And we also see that the number negative 5i solves the equation as well. Because here, if you square the minus, and minus times, minus gives plus, squaring 5 gives 25, and squaring I gives negative 1. So this also results in negative 25. Now there's another number which, when squared, gives negative 25, and therefore it represents another solution. The motivation for inventing complex numbers is to be able to solve negative square roots, because these arise in the real world, those square roots. So now I'm going to explain what a complex number is in rectangular form, and for that I'll draw one.
Standard coordination system, but instead of calling it X, standard
So the
coordination
y-axis
system.
is called the real axis, and the x-axis is called the imaginary axis. And now for each point on this two-dimensional complex plane, you can associate a number. So here's an example of a complex number. Here's an example of another complex number, and so on. There are complex numbers everywhere. If you happen to hit the real axis, then it's a real number. So the real numbers are a subset of the complex. If you happen to hit the imaginary axis, then it's a purely imaginary number, which is also a subset of the complex numbers. And here we have some arbitrary complex number, typically called z, and then you project down onto the real axis and project out onto the imaginary axis. And the number that appears here could then be called a, and this number could be called b. You could also call them x and y. It doesn't matter what you call them. And now you can write the number z in so-called rectangular form as a plus the imaginary unit times b. So when a complex number appears in the form I've outlined here, we call it a complex number written in rectangular form. Now, I'd like to introduce polar form. And to do that, I start by drawing a straight line from the origin to z. This will form an angle with the positive part of the real axis. I call this angle theta. The distance from there to out there, that's called the modulus of z. And it's written like this with vertical lines on either side of z. And the first thing I can tell you is that the modulus of z can be found by using Pythagoras on this right angled triangle. Indeed, it's the inside squared plus the inside squared. So the modulus of z has to be the square root of a squared plus b squared. So here's the formula to find the modulus of a complex number. And this angle here, where if the complex number z is in the first quadrant, then it's easy to find phi. You can find phi simply by taking the inverse tangent. So to find the angle phi, you just take the tangent inverse of the opposite leg divided by the adjacent leg, which means b divided by a. So here's the formula to find out
The angle. Ouch.
That's called one of the arguments, what's written there. You see, there are infinitely many. So the argument for the set of complex numbers, the arguments are equal to what I've found right here, plus an integer times a full rotation, meaning an integer multiple of 2pi. So here are all the arguments for the set, and there are infinitely many. That's one for every possible value of p, where p can be any integer. If you make sure to choose an argument that lies between minus pi and pi, it's called the principal argument, and then you write it with a capital A instead of lowercase a. So the principal argument for c, that's the angle theta, which satisfies the condition that it has to be between minus p and plus pa. So once you have found the modulus and the argument for a complex number, you can write it in polar form. And the polar form looks like this. The complex number z with just the modulus of z and then an angle symbol. That's how it goes. There, that's good then. So that's how you can write it. Sometimes people have come up with calling the modulus of z r, because it corresponds to the radius of a circle centered at the origin, which contains the number we're looking at. So you could write it with r and then the angle symbol, but you can also write it as an ordered pair, where you first write the modulus, and then you write a comma, and then you write the angle. That's another way to express it. And the coolest way to write it is all together. That's Euler's formula. You start by writing r, and then multiply it with Euler's number, and raise it to the imaginary unit times the angle. And it can look completely magical when you write it like that, and it really is. It's pure magic. But by the end of this course, we're going to prove why it's true that it can be written like that. So far, we've just accepted it and swallowed the idea. But the only thing your eye looks for when it's in exponential form is r and theta. The exponential symbol e, well, that's something we just accept, is there at the start. So what is this complex number? It's the complex number that's r away from the origin, rotated at an angle of theta. That's what the next number's about. Okay, to describe circles in the Gaussian plane, you can do it like this. One reads the set of complex numbers that lies at a distance, is located at a distance from the complex number A. So this right here is actually the equation of a circle, no? Because these are all the sets of complex numbers that maintain being a distance r away from the complex number A. So there's a diagram that goes with this story, which looks like this. A is the center of my circle. So this is a complex number called A. Normally A is down here, but it's not this time. Because here A has a real part, which I now call X, and an imaginary part, which I call Y. So A is a complex number, X plus IY. And now I can draw a circle with a center at A that has some radius R, and all C's that lie on that circle, they will satisfy that equation, and that's why you call that equation the equation of a circle. And the way to understand this is to delve into what those two signs from real numbers mean and begin to comprehend them, and then you'll see that this ends up describing a circle if you do it. For example, if it says like this, the numerical value of x minus 2 equals 5. The interpretation of this is, can you find all the real numbers x that are at a distance of 5 away from the number 2? So we can also draw this, but now it becomes a number line we draw it on. So we draw the number 0, and then the number 2, 1, 2, and then we need to be 5 away from 2. Let's say, here is 5 away. So here is 5. And so we end up at 7, which means this number solves the equation. See, 7 minus 2, that's 5, and the conventional way to write it is 5, it's 5. But there's another number besides 7 that is 5 units away from 2, which is the number -3, possibly right here. So this is also 5. There are like 2 numbers that satisfy this equation, and you could find them by placing a compass at the center and drawing a circle. Where the circle intersects the number line, that's where you get the solutions. But with complex numbers, because they lie in the plane, it's all the numbers on the circle. And that's why you can use complex numbers to describe circles in a very neat way. What's next? What's next? Okay, now I gotta go.
For the complex exponential function.
So that means I'm looking at a function that takes a complex number as input and also gives me a complex number as output. So we can sort of imagine that I have a version of the complex plane right here. And I've got an x and a y axis, a real and an imaginary axis, but now I'll call them x and y. And here's a set of complex numbers. That's my input. That there is my input. And then there's this thing about the output. And this is z. And here's x. Hey there.
So z equals x plus I.
And then I send z off with a function. So it goes on a space journey. We launch c into space with the function f. And what does f do to c? Well, it takes c and uses it as the exponent on a base number. And out of that comes a new number, which I've decided to call W. So this is just something I came up with. It's a new complex number, which I can then draw over here on a new version of the complex plane. And to avoid confusing it with the other one, I'm not calling it XY, but U and V. So we have a U axis and a V axis, and somewhere over here, that's where W lands. It could be that W lands right here. Called, and then I can draw here and say that here lies W, but W is now called U plus I times W, U plus 4. So we see that we have an input, we send the input off, and then it lands over here in our output.
So this is our output plan.
And over here, we've got the output Gaussian plane, and this is our input plane right here. So all the inputs to the function exist in this plane, and all the outputs live over in this one. And the way they go from one plane to the other is that they're propelled by the function f. So let's see how that happens. What does f of z yield? So if it corresponds to e raised to the power of z, what does that give us? Well, remember z was x plus I times y, so this must yield e raised to the power of e.
X plus EV.
So we can rewrite this using the rules of exponents to e raised to the power of x times e raised to the power of I times y. And this right here is a complex number.
This is a complex number W.
And if you want to find the modulus of w, meaning the output, it corresponds exactly to e times t. So underline that twice. Now I know where the modulus is,
And if you want to find the argument,
and there is w, then it corresponds to y. Or y plus an integer times 2 pi.
those are all the possible arguments for W.
And by the way, w can also be written in rectangular form as u plus I times v, where u is this distance. And w here represents this distance. I was also going to give an example. So I also just need an example. So it could be that I have a z, which is 3 minus 4i, and I want to find e in the z. So that just gives us e raised to the 3 minus 4i. And I split that into e3
Times a to the power of minus I times 4.
And now I can read directly that this here is w. So this right here is my w. That's my output. And I can now see that the modulus of my output becomes this number. That is e3.
And all the arguments for W, it'll be minus 4 radians.
Plus an integer times 2p. So that's the answer. Here's the answer. And if you feel like it, you can convert it to a proper angular form and write it as u plus I times v if you're up for it. Okay, so the last part of the question is the one you just saw, where I will talk about the complex exponential function. And so there are some videos that Denby is making right now, where I'm standing and giving an example of how one could approach the exam in this subject. It's made more advanced. They're already on YouTube from the last time I taught the course. But this is the first time we're recording the entire class. So I don't think I'll do it again. We've done that. The new thing here is that we're recording all the teaching. But now I'm making just a quick exception to that rule. The last thing I'm going to talk about is the complex exponential function. And that's what I need to ask. Given that I know z, so this right here is a known complex number that's over here on the right side. Can I then find w? If I can do it, what have I effectively done? I've taken the complex logarithm for whom? For z. I have indeed found w. Look, if you want to find w. So w would precisely be the complex logarithm of z. So this is what this story is about. How does one take the complex logarithm of a known complex number set? So
They
we
are
imagine
fighting.
that it's well known.
It's written in form of
Our gang is the best. And just for the sake of good order, let's say that this phi lays between negative p and p
and therefore phi is a principal argument for z. And what I'm looking for is w, and let's say that w, the one I need to find, is written in pure angular form like this. So if I need to find w, who do I need to find? X and y. So I've got w. So I take this expression from w and put it in w's spot. So this is what's going to be written here. And in the equation spot, I write this in Euler's form, which strengthens z. This rewriting will essentially be like an apology, inserting e in xt, multiplying a by I and y. On the right side, I'm just copy pasting after myself. And now I can see that if this equation is to be true, and these two complex numbers are to be equal, then they should be the same distance ahead. So they must have the same measure. So this gives rise to two equations. One of them is that e times extra should equal r. But it wasn't r that I needed to find. R was what I already knew. What I needed to find was x. So now I have to solve completely for x. And to find x, I need to take the real logarithm of big R, which of course is only possible if that is not 0. It can never be negative because your modulus can't be negative. But it could be 0, unless one remembers to say up here that z is not 0. But for all other numbers, you can take the complex logarithm. And finally, I can say that y should be phi plus a whole number of complete revolutions, except for an integer number of complete revolutions. But now, as we can see, here I found x, and here I found y. There's only one answer for x, but there are infinitely many for y. What does that tell me? There are infinitely many complex logarithms for z. Indeed, 1 log 1 for each chosen value of the whole number p. But if you make sure to choose p in such a way that what you have is the principal argument, then you call it the principal logarithm, which is written with a capital L. So what then is the principal complex logarithm of a complex number set?
It's x plus y at least.
And I found x was the natural log of I, and y was phi, because I had chosen phi as the principal argument. So here it shows how to define the principal complex logarithm. Now let's see how much time I've spent. 17 minutes in. I like to give an example because you have 30 including rotation. Let's just take an example and then we'll wrap up. Let's say, for example, it says, can you find w such that the absolute value raised to the power of w equals 5 times the absolute value times negative I times pi over 4. So it's just a spoken example I'm making up right now. And I hope that all makes sense to you. So if I need to find w, what should I do? Well, I know that w is x plus a times y, so that's what I can start by writing down. So basically, I just need to find x and I need to find y. And I should find x like this. We had concluded that here. So instead of x, I can write the natural and real logarithm of 5. Because that is the modulus of c. So given that the modulus is d5, we need to affix 5. So now I've taken this one, and I need to say plus I times y. Plus I times y. But y is the angle minus pi over 4. Plus p times 2p. So this is the answer. And how many answers are listed here? So what is this? This is all of the infinitely many complex logarithms of c. And you would write that like this. That's enough for no. So remember, when it says log, it doesn't mean the increasing logarithm when you're dealing with complex numbers. When it says log, it means all the conceivable infinitely many complex logarithms. If I want to reveal, it means all conceivable infinitely many complex logarithms. So I just need to write the natural log of c aligned with the natural logarithm of 5. And I just have to make sure that this becomes a principal argument. And what's necessary for this to become a principal argument? P just has to be 0. Because if P is 0, then it's minus pi over 4. And that's between minus pi and pi. So it is a principal argument. So plus I times negative pi over 4. And that, looking a bit silly, is where I move the minus out front. And I believe he just sees it clear as ice.
So we've got to write a nice obligatory note there.
This is the principal complex logarithm of c butterfly, donkey.
That was it.
Woof it. Now I'll stop the timer.
Sleep. You might not be able to see all of that because I've been through it many times already. And how does it work leading up to the exam? Well, it works like this. You try to explain things as best as you can. And if you get stuck, I'll ask a little to help out, to get you back on track. And if you don't manage to say what you know, I'll also ask to make the examiners aware of that. Then they'll say they can do that too. That thing. And with just a bit of polish, it clicks into place. So I never ask questions in order to tear things apart or anything like that. I'm never trying to cut you down or anything like that. Think of me as a backup. I'm here to help you demonstrate what you know. But of course, if you don't know, it can feel uncomfortable. But that's not my fault at all. I do the best I can. So make sure you know your stuff, because then exams can actually be fun. Because we ask questions, and if you just learn it completely so that you can recite it without liking it, then we'll dig deep with questions. All right, you're clear on that. I'll explain that in a moment. That's something you can't get past, and I can't comprehend it. So that's what we're looking for. Understanding, not just rote learning. But just because I say that exercises don't help, doesn't mean they aren't incredibly beneficial. The more you practice, the better you get. Because math is a subject that requires practice. 10% talent, 90% practice. That's just the way it is with math. And then there are very few people who fall outside of that generalization. There are some who can learn everything in a few days, but there aren't many like that. And then there are some who never learn, but fortunately, there are quite a few of those. So all of us normal folks can learn it if we want, and if we're willing to put the hours in. We can. I've never seen it fail. So, if you just make sure you're on top of it, things will go smoothly here.
Only stay away if you can't make it.
What time is it? We don't need to take the break just yet. So let's get started on a new topic. Yes, you can't do that yet because I haven't posted them yet. But Mikkel did get a glimpse of them earlier in the Word file that outlines the questions I have on my computer. And I would guess that about a month before the exam, you'll get to see them. But if I show them right away, some have the tendency to ignore everything that isn't in the questions. And that's not the intention. Mads? What's in a name? Fear and theater are two different names for the same thing. It all depends on what mood you're in when you dip into it. But it's an angle. Yes. And p is an integer. So p belongs to the set of integers. If p is 1, it looks like this in your mind. If p is 2, it looks like this in your mind. And so on. And you can just swap them around as you like, as long as you know what you're doing. Well, if you don't fancy those Greek letters over there, you could also call it V for angle. I think they look so tasty, so that's why I like those Greek trousers over there. It's those little joys you need to have when you're teaching. There's room for a little bit of emotion. Yeah, it's completely irrelevant, because it's just the name that says something about an angle. Okay, thanks.
Article 8, new subject.
We're about to start with the introduction to linear algebra. In theory, I could just dive straight into linear algebra, but experience tells me it's better not to, and instead start by assuming you don't remember everything you've learned. Let's review some of it first. Let's do a little refresher on vector arithmetic. Some of you might have heard this before, so you can just enjoy the joy of recognition. Others may have never heard it or not explained this way before, so you can also take pleasure in a different kind of joy, the thrill of something new. Let's dive into it. The first heading is the concept of vectors. And because all this is background knowledge needed to start a study on snow, things are moving along at a pretty good clip now. If things get too fast, I'll just slow myself down. What is a vector? There are certain things in nature around us that can be described with just a single number, and a single number is enough. And that's the end of that story. For example, how much do I weigh? 85 kilograms. How tall am I? 1.86 meters? A single number suffices, so now you know my height. How far is it to my home? 73 kilometers. A single number suffices. So certain physical quantities can be described with just one number, and that's enough. But some physical quantities can't be described with just one number, and those are called vector quantities. So what's an example of a vector? The gravitational force on me, which is actually what's known as Jim's weight. It's the force of gravity on me. That's 85 kilograms times 9.82 newtons per kilogram. So that's about 850 newtons downwards. That's a vector. 850 newtons downward. That's a vector because I'm specifying downward in addition to the 850 newtons. A vector has both magnitude and direction. But a scalar that is just a number is simply a magnitude. Okay, so how far is it to my place? 73 kilometers. Which direction do I live? Now it's a vector, and the vector is 73 kilometers long. So certain physical quantities also require knowledge of direction, and that's what we call vectors. So here's an example of a vector. You draw it as a straight line
with an arrow on one end, so it goes that way.
and the distance from the start of the vector to the end of the vector, that's what you call the vector's length. That's the distance right here. That's the length. I've got a long way to go before I'm a joker. You write a vector with a letter and an arrow over it. If you're kind of lazy, then you write it like this. And if you're super lazy, you just write it like this.
But since we're very diligent, we write it like this.
If a vector is in 2 dimensions or 3 dimensions, we call it a geometric vector, because then it can be drawn. And if a vector has more than 3 dimensions, you write it like this. So it's an ultra lazy arrow with just a line, and now it has to go underneath. This right here is a vector. It has more than 3 dimensions. We don't know how many more, just more. So with more, 3 dimensions. And now it's not a geometric weight anymore, because you can't draw it. Unless you're a 4-dimensional space creature, then you could draw it. But we can't do that here, in this reality we're in. A vector has coordinates. And that means if you draw vector A here. And I'll tell you how far it is from here to here. So that direction is called the x-coordinate. And perpendicular to that, you call it the y-coordinate. And these 2 numbers can be positive, negative, or 0. If the number A1 is positive, I go this way. If the number A1 is negative, I go that way. If the number A2 is positive, then I go this way. If the number A2 is negative, then I go that way. So I can see that depending on where I start a vector, I can head in any direction, just by adjusting the numbers A1 and A2 with their signs. And these 2 numbers can be called coordinates. And you write it like this. A1 over A2. And because there are 2 coordinates, and only 2 coordinates, it is called a 2-dimensional vector. The length of a vector, as we've explained above, which is essentially the measure from the start to the end of the vector, can be found by using Pythagorean theorem, because the square of one side plus the square of the other side equals the square of the vector's length. And you write it like this. The length of vector A squared is equal to A1 squared plus A2 squared. The first coordinate squared plus the second coordinate squared. And if I want to find the length of vector A, then I should take the square root of both sides. So, how do you find the length of a vector? You take the square root of the sum of the squares of the coordinates. And if you want to impress your examiner, that's how you say it. The length of a vector is the square root of the sum of the squares of the coordinates. So you could just say the square root of the first coordinate squared plus the second coordinate squared, if you find that easier. So that's how you find the length of a vector. Vectors can be added together, and vectors can be subtracted from one another. So now, on to something new. Welcome, and good to have you with us. It's called the magnitude and difference. If I have a vector here, which I call vector A, and if I have another vector here that I call vector B, and if I've made sure to draw it, so they both start at the same point. That's the thing, actually. You can start a vector wherever you want. But once you've started it, there's only one place a given vector can end. But you can choose where to start it. And if we choose to start it from the same point. So they figured out that if there are forces acting on a car, for example, and there is a person pulling that way on the car with a force of as many newtons as the distance from here to there. Let's say it's 10 in distance. Then the force is 10 newtons that way. And if there is a force acting in this direction, which is 15 newtons, you can't just say 10 newtons plus 15 newtons. It doesn't work that way. It doesn't mean there are 25 newtons pulling the car. Why not? Because they're not pulling in the same direction. If they're pulling in exactly the same direction, then you could just add them together, the forces. But now that they form an angle with each other, you just can't. And experiments have shown that if you grab a car, let's say it's out in deep space, and we've thrown a Tesla out there, one of Elon Musk's cars, I believe he did send a Tesla out there once, and it's floating there in deep space, and suddenly, two magical forces act on the car. One this way at 10 newtons, another that way at 15 newtons. What does the car do then? It accelerates. It starts accelerating. Which way does it pick up speed? Not that way. Not that way either, but something in between. And what you find is a sort of middle ground, like this. We'll just take a little quarter of an hour, where that one is just as long as that one, and parallel to it, and where that one is just as long as that one, and parallel to it. And where they intersect, that's where you now draw a vector that ends. So I need to draw a vector that starts where the two began and ends out there at the tip on the diagonal of that parallelogram. And now I have the experiment to show that this is the direction that Tesla accelerates. And because that's the direction it accelerates, that's how we define vector direction. So this right here is the vector A plus B. The method for adding vectors together is called the parallelogram rule. I can never remember how many elderly there are in the digiparallelogram, but there's like a ton of them. So there are 3 to 4 pieces. I've drawn 4. I hope that's correct. But there's a hologram. Here we have grammar rules, after all. You can also add vectors together in another way. Basically, if this here is one vector, then I scale it off. So I can just draw vector B as an extension of vector A. So first I draw vector A, and right where vector A ends, I'll just draw vector B starting from where A ends. And this vector now starting where I started and ending where B ends, this vector, it's the sum. That's a plus B. That's another way to do it. That rule is called the parallelogram rule. And this one down here is called the sharp angle rule. Or I don't know if it actually does, but that's what Walter Lewin calls it. He's from MIT and has been teaching there for 40 years as a professor. So I guess he's allowed to invent the name for a rule. He calls it the heads and arrows method, or the tip to tail method for vector addition. And then it's all set. It's really easy to add them together. Adding vector A to vector B is quite straightforward. You simply take the first coordinate of vector A and add it to the first coordinate of vector B. And then
you take the vector
and add it to vector B's second coordinate. And from that, we get a new set of coordinates, which is the sum. So it's as easy as it can be.
It was fun.
So there's a difference.
How do you subtract vectors from one another?
And it's almost just as easy. Because if I have to say vector A minus vector B, so you cleverly say a cart, that's just vector A put together with B, but with the opposite sign. Of course, that needs to be interpreted. What does it mean?
Yeah, just imagine that this is weight 3, and this right here is vector B.
And you want to figure out B. So you just take a negative B and rotate it 180 degrees, so it points the other way. Now you have negative B.
So I'm just making a new drawing. That's A.
And since it positioned itself there as minus B, then this must also be minus B. And now it's easy. You just have to add minus a and b, or minus a and minus b together, just like we did before. So I grab a parallelogram, and that edge starting over there and ending here, it's a plus negative b, so therefore it's a minus b det der med, so what is the vector AB? Listen closely now, because what's coming next is usually not found in the books. What is this vector, the AB? It's the vector you add to B to get A. So if I take that vector, I move it over here, it starts there and ends there. So A minus B is the vector that you can add to B, and then you end up with A. So take B and add A minus B to it. So it's not so strange that you get A, because B minus B cancels out. So this is the vector you can add to vector B to form vector A, and you can clearly see it on the drawing here that this is the vector. If I first go from here to there, and then from here to there, where have I effectively gone from and to? Well, I started here, I ended there, and then I walked along it, and that was A. So always remember to think about what you found, not just use a rule. What is it you've discovered? You found the vector that when added to B forms A. So that's almost like addition and subtraction. If you know the coordinates, you can easily find vector A minus vector B. You just need to take A's first coordinate and subtract B's first coordinate, and then take A's second coordinate and subtract B's second coordinate. That's how you do it, if you know the coordinates. So that was vector addition and subtraction. Now I can see in your eyes that this would be a good time for a break, because you're starting to nod off. So let's take a 10-minute break, grab a soda, and then we'll continue. It wasn't that long of a sleepy weekend to take a break now, was it? Okay, I know you guys are looking forward to the weekend, but we'll keep going for a bit longer. So we discussed the vector concept, sum or difference. Now let's talk about scaling. Vectors can be scaled, meaning they can shrink in the wash, or they can be blown up by a compressor. If this is a vector A, then that's a vector B. So if I multiply that vector,
It's not
I
like
get
a
a new
train.
vector that's just twice as much.
Take a look here.
So this is twice the vector A. If I take a vector and multiply it by -1, it has the same length as before, but now it is pointing in the completely opposite direction. That's exactly 180 degrees the other way. So that's the negative vector. If I multiply a vector by a half,
So it gets shorter than it was before, but in exactly the same direction.
Nästan som med drawing. Mش عارف صح. أزنا.
if it was 3 long, it's still 3 long, but just pairs the other way. I think that answers your questions. Yes, a distance can't be negative, but if you multiply a vector by -1, it simply reverses its direction. So the sign can be used to change the direction of a vector. Now let's say you take a random real number k like this. It means here that it's a random real number. If you multiply it by a vector, then it simply changes direction with -1. So the rule says that you just take the number k and multiply it with the first coordinate. The new number you get is the new first coordinate, and you do the same with the second coordinate. And out of this comes a new vector with a new length. If k is greater than 1, then the vector has become longer. If k is between 0 and 1, then the vector has become shorter.
If k has not
7 is between 0 and -1. So the vector has become shorter, but it's pointing in the opposite direction. And if k is less than -1, then it's a bit longer, but points in the opposite direction. Are you all following this? So if you now ask, how long is a scaled vector? So when we talk about the length of a scaled vector, what we're asking is, how long is the core of it? And the core is a vector. So it appears that the answer is to take the numeric value of the scaling constant. See? Because the length can't be negative. So if you multiply by -7, you need to remove the negative sign from that -7, and that's what the numeric sign is for. Then you multiply it by the original length of the vector, and that gives you the answer. If a vector is exactly 1 unit in length, we call it a unit vector. That was the next topic I was going to talk about. So a vector with a length of 1 is called a unit vector. And there are 3 particularly important unit vectors you need to know. They are called I, j, and k. And these are vectors, so remember to put vector bars on top.
It is 3-dimensional vectors.
They are geometric vectors.
And that weight called I, it moves purely in the x direction, so it's called 1. And then it doesn't move in either the y or z, so it's called 1 over 0 over 0. And that one, it moves purely in the y-axis direction, so it's called 0 over 1 over 0. And it moves purely in the z-axis direction, so it's called 0 over 0
And
over
if
1.
we draw this in space, then I can draw a 3-dimensional coordinate system right here.
And you'll need to practice drawing this before your oral exam. Such a clumsy coordinate system. But this vector that starts right here and goes 1 unit in the direction of the x-axis, that's I. It doesn't have to start yesterday this year, but it can. And if it does, it'll look like this. And the vector that's 1 unit long in the direction of the y-axis, which could be drawn here, is j. And this one laying right here, cruising along the z-axis direction, which is a unit, that's k. And we will get back to that later when I will explain about the cross products. If I now have a vector that isn't 1 long, but might wish it were 1 long, such a hopeful vector, let's say I have a hopeful vector called vector A, and it's 3 over 4. So now I'm back in 2 dimensions. How long is the vector then? We've just learned that the length is a vector. So you find it by taking the square root of the sum of the squares of the coordinates. So that's 3 squared plus 4 squared. And here we are back to the 3, 4, 5 example that he's so fond of. So that's 9 plus 16, which is 25. Square root of 25 long, which is 5. So it's the 3, 4, 5 example, right? So this hopeful vector, it's actually 5 times too long to be a unit vector. Could we do something slick to that vector to make it unit length? Yes, we could scale it. But here's a fact you should know.
0.5.
If you multiply a vector that is 5 units long by 1/5, it becomes 5 times shorter than it was. And suddenly it's not hopeful anymore. Now it has fulfilled the typical wish to achieve. It's become 1 unit long. And that's what you call a unit vector in the direction of a given vector. And you write it like this. Now I'd like to make a unit vector in the direction of A, which is A, that there. And what do? I take the reciprocal of the vector's own length. That would yield the 1/5 in this example because the one down here was 5. And that number, just shake it off with that. And there you have it. Isn't that clever? It always works. If you have a vector that is 5 units long, it is 5 times too long to be a unit vector. So you simply multiply it by 1/5.
And this is how you form a unit vector.
In the direction of a given vector.
Let's take an example so it doesn't all get too abstract. Let's get more specific with an example. Let's say I have a vector called 2 over 3. Now the numbers aren't as tidy, but I just want to show you that it still works. Can I make a detour? It's too long to be a unit vector. If I need to find its length, I must take the square root of the sum of the squares of its coordinates like this. Here we have 4 and here 9. And 4 plus 9 is 13. So this vector is the square root of 13 long. That's a factor.
1 over square wire.
To be a unit vector. So therefore, I can find a unit vector in the direction of A by taking 1 over the square root of 13 and multiply that by the vector, which is of course 2/3. And as we just saw, when you multiply a number by a vector, you multiply each coordinate, first and second, or third, if it's a 3-dimensional vector, by that number. So you don't multiply the number by 2 and then by 3. This means that my vector will have coordinates 2 over the square root of 13 as the first coordinate, and 3 over the square root of 13 as the second coordinate. So if everything went well with my calculations up here on the board, then this should be a vector that's 1 unit long. So that's well tested. Is that vector 1 unit long? Let's try to find the length of this hopeful unit vector, which is in the same direction as a... So all I have to do is take the square root of the sum of the squares of the coordinates. That is, I need to say 2 over square root of 13. So what I'm saying is the square of 10.
3 over 13 squared. It needs to be put in a.
And then we just need to figure that out. We can just figure that out in our heads because 2 times 2 makes 4. And then there's 13 times 2, which makes 26.
So here there will be a 4, a 13, and a 1.
And 3 denotes 9. And card number 13 to the second power is still 13. Now I can count how many 13s I have. I have 13s, that's what it is. The other must have added a 1 and scored a 1, but that's a 1 itself. So it's good enough. That was a unit vector. And besides that unit vector, what's cool about this vector is that it probably points in pretty much the same direction as it does. It's clever. It's a useful tool in mechanics. It's really handy in mechanics. It's quite clever to find a vector that's long and points in the same direction as a given vector. Okay. Now I'm going to talk about direction vector and normal vector. So that's been taken to the next counter.
So the heading is now direction.
Good evening.
Waiters and normal waiters.
Okay. A direction vector for something is a vector that has the same direction as that something which it is the direction vector for. Here's a straight line alone. Here's a vector that has the same direction as the line. Since it's parallel to the line, we call it a direction vector, and it's the first one that came to mind, so it's called R1. But all vectors parallel to the line are equally good as direction vectors for the line. So here's another vector. It starts here and ends there, and it's just as good as a direction vector for the line because it's equally parallel. And here's a third one. So you can see, no matter how long the vector is, whether it points this way or that way, as long as it's parallel. This means that if it forms an angle of either 0 degrees or 180 degrees, then it's just as good as a directional vector. So now, so I hope that you understand the concept. A direction vector is one that has the same direction as whatever it is a directional weight form, which means it points the same way as the line. Notice that a straight line doesn't have any directional flow. There isn't an arrow on the loan, right? The loan extends infinitely in that direction and infinitely in that direction. So there's the concept of a normal vector. If I have the loan here, and now I have a weight that stands perpendicular to the loan. So when you have a 90-degree angle here, you call that vector a normal vector to the line, because normal means perpendicular. And since this is the first normal vector I can think of, I can call it parar n to 1 r. So on n1n is a normal vector to the line because it's perpendicular to it. But it could also have been here. That's completely irrelevant, and its length doesn't matter. So that's another example of a normal vector, which we can call r n2r. And it is just as valid as a normal vector as r n1r is, because it's still perpendicular. So here's a third example of a normal vector for the line.
And it doesn't even matter that it's pointing the other way.
Because it still stands perpendicular, here is a third example of a normal vector for the loan. We just covered the concepts of direction vector and normal vector. So now let's talk about the concept of position vector. A position vector for a point is the vector that points to that place if the vector originates from the origin. So imagine that you have a coordinate system. Now imagine you got a coordinate system, and in that coordinate system, is there a room? So this here is a place,
And I call that place P because it's a point.
the vector now pointing to that point, starting from the origin, snap, that vector is called the position vector for point P.
if P has the coordinates x and y, then we can say that it's the x coordinates that have the value y, and it's the y coordinates that have the value y.
So this is how you write pxy like this. So this vector here, which is typically called the r vector, it doesn't stand for direction vector now, it's just an r. Then the position vector r will have the coordinates x over y, because a position vector for a location has the same coordinate set as the point itself. It's just written differently. They are written horizontally in parentheses when it's a point, and they are written in square brackets and vertically stacked when it's a vector. So at least that's how I do it, because some mathematicians, they don't use square brackets when they write vectors, but curved ones.
But I find it a bit easier to make them look nice on a board.
There's room for feelings.
So that was the concept of direction vector, normal vector, and position vector.
Now here comes something we really need to get.
Yes, I understand.
Because everything I've mentioned so far, you've heard before, and I think most of you have grasped it because it's simple. But what's coming up next requires a bit more thought before you can truly understand it deeply. What is a dot product and what is a cross product? And especially with the dot product, there are many people who, when they come here to begin their graduate studies, haven't grasped anything about it at all. They can plug into a formula and get a number out, but they have no idea what they're doing. So we need to fix that now. So up here, for the first time, you're going to truly understand that scalar multiplication is profoundly important. And I'm pretty sure that goes for all of you, because I didn't grasp a single thing after high school, despite getting good grades. So I still didn't really understand what I was doing. It was actually much later that I came to realize what scalar multiplication really is. So let's just tackle this story in the way that engineers or physicists think about it. So the heading now is scalar product. Vectors cannot be multiplied. Forget about that for today. They can. Complex numbers can be multiplied, but vectors cannot be multiplied. They can, however, be dot producted. And if you dot two vectors together, you get something that someone decided to call a scalar product. So let's just start by doing what it says in the math book, and then think afterwards, what does it mean? So what does it say in a math book? It says that if you have a vector A, and it has the coordinates A1 and A2,
And then you have another vector B with coordinates.
Bravo 1 over Bravo 2.
So you can stamp them, says the math book. You can't multiply them. You can stamp them.
So what's a bit confusing is that the symbol looks exactly like a multiplication sign without being one. So what you're seeing there, that isn't a multiplication sign, it's a symbol. And many Americans, to point out that it's not a multiplication sign, they write it down here. But that looks terrible. So we write it where it belongs. But it is indeed just a dot. And how do you dot two vectors? Well, someone came up with that, and it might just seem like pure invention, but it's not. There's a really good reason for doing it, and it's coming up in just a bit. But what should you do? You should say this times that plus this times that. And by times, I mean multiplication. I'm not talking about dotting. Because by that times that, we're talking about two numbers. It's a real number, and real numbers can be multiplied, but vectors cannot.
So
What's
hello.
D1?
Hey, A2 times B2. So this is how you dot two vectors if they are two-dimensional, both of them.
What if they are three-dimensional? Then you just take A1,
One
B1,
plus A2.
C1.
Noted.
If it says A2, A1,
A1.
then
and
you have
A3
to say A
here.
plus A2,
It is what it is.
B2 plus A3, B3. That's just how it was. 3 coordinates in
Oh,
each. They were
but if it's
sort of
3D
like
win?
vectors.
They can go up all they want when it comes out of my
I
mouth.
just need to say
Cool, right?
sorry for a moment.
But if they are two-dimensional vectors, you do it like this. And what's the result? If it's a number and that's a number, then their product is a number. And if it's a number and it's a number and that's what it is, and you multiply them, then it's also a number. And a number plus a number gives scalar. So when you multiply two vectors, you don't get a new vector, you get a number. So far, I'm just saying what's in the math book. You don't get smart from it, you just learn to do it. That number can be greater than 0, less than 0, or equal to 0. Okay, let's give it a shot. We still don't really get what we're doing, but now we're going to try it anyway. So here's an example. Last year rolled off. It's called 2 over 3.
Well, if
sell
it's
it.
gone, then
It's
pray
called
for it.
3/5 because it's so inventive of you guys when it's version 2, 3, 4. So if I'm going to coin those two, then I have to say A. Subtract it with B, that makes 2 times 4. And by that, I mean multiply the number plus 3 times 5. Let's see if I can figure out the calculation. What does it say? 8 plus 15, that's 23. So that was the speech.
And that number was larger.
So what can the brain think about? So I found it, I handed it in. You learn a rule by heart, and then they say, yeah, that's fine, good. You've applied the rule correctly. But what have I actually done? Like, I totally don't get why anyone invented this. What does it mean? What does the number 23 have to do with vector A? What's it got to do with vector B? And how am I supposed to use this in the real world? And I actually wish I could tell you that it's absolutely useless, because that would be kind of funny. But this, in fact, can be used for absolutely
Something
nothing.
we've always used as engineers. Dot products. Now let's try to understand what is
We're
this?
working with that dot product. Do I have room for a bit of the story here?
So
Not
that
really.
will be on the next board. So here comes board 11. So the heading is still dot product. The headline is still dot product. And now for the secret. The dot product between two vectors is a measure of how much the vectors assist each other. All right, I'm there. I'm going to write that down. Dot products between two vectors. Is a measure of, and this is like a very physicist type of statement, this one. I mean, a mathematician, if he were dead, he'd turn in his grave if he heard me say this, but we do need it. So we're interested in understanding, even when the
What does it
neighborhoods
mean?
are.
The scalar product between two vectors, that's the goal.
Why? To what extent?
Two vectors.
And now I'm going to use a word that really doesn't
It
belong in either.
works. It really does. Helping each other.
I really shouldn't be doing this. So if anyone's watching the video and it's about math or physics, then it's not
Really bad stomach ache, right? It helps.
But what do I really mean by this?
It was right here.
Take a look at this. Here are two vectors. This is vector A. And here you are, Abaxer. They really help each other out a lot.
We help each other as much as we possibly
They
can.
really help each other out. It points in the same direction.
And two vectors that are going in the same direction.
And in my neck of the woods, it means that they help each other out as much as they can. Because if you have to push start a car where the starter isn't working, it's really stupid for one person to stand behind the car pushing that way, while another stands in front of the car pushing the other way. I think it makes sense that they help each other out, the two pushing. But if both of them push in the same direction on the car, then the two force vectors help each other as much as possible.
If that's the case,
Alternatively,
you should learn to act
the question
the
will
fool
likely be
as
asked
best you
if
can.
what I've written here is true, and indeed it is.
Because if this vector is 3, then this vector is 3, and if this vector is 2, then this vector is 3.
And now we're moving on to lever streaming. And this weight.
Here it is.
So
We're going to say 5 newtons.
So that's 3 newtons, and that's 5 newtons.
So Scalabro would rev up times 5.
it's 3 times.
It's 15, and it's exactly like that
That's
one.
what it comes down to if you do the math.
If two vectors point in the same direction, then the dot product can never be greater than the length of one times the length of the other. And that's exactly what it becomes when they point in the same direction.
So this is a case of the max
Into a measured dot product. So in Hunter Canaan, you can almost figure out when the dot product is minimal.
it's in a situation that looks like this. Here's one vector and here's the other. Now the two vectors are pointing diametrically, which means in exactly opposite directions. And now the dot product can't get any smaller. How small does it get then? If one is 3 neutrons long and the other is 5 neutrons long, the scalar product becomes -15. So if you see a dot product and it yields a negative number, what does that tell you? They don't assist each other, we believe.
Yes, they counteract each other to some extent.
So if one vector is 3 units long and the other is 5 units long and it gives us -15, what do we know? They're working against each other as much as possible, pointing in completely opposite directions.
Amen. And so on. So this right here, this
Minimum scalar product, which I've drawn here, of course, there's also the possibility that the two vectors don't care about each other at all. They don't work together, but they don't work against each other either. They're completely indifferent, so they're at right angles. And if this is one vector, vector A, and if this is the second vector, vector B, and if here is 90 degrees, then one can basically say that vector A is completely ignorant of vector B. It neither helps nor hinders it. An example that's almost true in the real world is when you need to push start a car with two people, and one of them hops on and sits on the hood, just chilling out.
And the other person goes around to the back and tries to push start the car.
So the person sitting on the hood affects the car with a downward force due to increased gravity.
So he's exerted force on the car, a measurable force downward.
The person behind is pushing the car in the driving direction, and he's pushing perpendicular to the other one, because hopefully they are on a level surface, and now it's not. It's tough anyway to push a car uphill to get it started. Maybe downhill is easier, but let's say I disregard the level ground, then the one pushing from behind, he will push horizontally, and the other one will push downwards, because gravity is acting on him, and he's sitting on the hood, so he's applying a force downward. In that situation, there would be dot products. And that means the two vectors are disregarding each other. So they neither help nor counteract each other. Therefore, the scalar product here is 0. So now you've got an idea of the dot product. I hope that you can now imagine that what I'm saying must be true. Here is a number line. And on that number axis, scalar products lie somewhere. From where to where? Somewhere there has to be a 0, where the two vectors are perpendicular to each other. If I am right here, let's quickly make a drawing that looks like this.
And 90 degrees.
If there's a position to wind against each other, then the lab should open now.
And somewhere out there, we're at the max, where it can't get any bigger.
And if we're out here at max, where it can't get any bigger, then the drawing looks like this, vector A, vector B. Now they are pointing in the same direction. A good spot in the same direction. And just as far away as the max is from 0, that's how far away the MN should be from 0 as well. That's a deliberate choice. We want to be fair to 0 and say you get to be right in the middle. We shouldn't favor positive numbers. And because we don't want to favor them, we take this distance here and just copy paste it over here. And here is the smallest a dot product can give.
And when does it end?
It ends if the drawing looks like this.
And that's vector A, and that's vector B.
And what if you place something from here to there, then the drawing looks like this. Now it's partly pointing in the same direction. And if you place it like this, starting from here, they point this way. Now I'm going in the opposite direction, but not directly opposite, because I'm an exaggeration. So now we start to be able to explain much more clearly what a scale product should be. It's a number. What number is it? It's a number that measures how the vectors operate.
It's how it's oriented in relation to each other, whether they help, oppose, or are ignorant. These are the three extremes.
Those are the three extremes. Extreme help, extreme opposition, and complete indifference to each other. And then there's everything in between. And the dot product can give us anything from here to there, but it can't give us anything outside of that. The maximum value a dot product can yield is the length of one vector times the length of the other vector. It can't produce a number greater than what's been defined. So if one is 3 units long and the other is 5 units long, the maximum it can be is 15 units long. What's the minimum it can produce? Well, it can never result in anything less than the negative of one vector's length times the other's length. It just can't. So if one is length 3 and the other is length 5, then it can never result in less than negative.
Minus 15. But we can't
Everything
do that.
from negative 15 to positive 15 if one is 3 long and the other is 5 long. So you can get all numbers from here to there just by laying down and rotating one with respect to the other and calculating their dot product.
Can you see it?
That's how you should think when you're pitching a product.
So you can use it in physics and mechanics.
So you can prove it. And that's what you've
That was
done.
back in high school, so we won't bother repeating that proof. It's quite simple, really. But one can prove that the dot product between two vectors.
It's
Layer it with one piece, layer it with
Yeah.
another piece.
Then
multiply the cosine by the angle in between. Now I call it V because you can't quite manage it.
that could be the angle that was here, or the angle that lies right there on this drawing. You can't prove this.
And now you'll see why it makes sense. Listen up now.
If A and B choose
So
themselves,
each point in the same direction. So what's the angle between them?
they just have one act in the same direction.
Nothing. Smell that? Nothing.
1, so there's a 1 right here, and when you multiply by 1, you don't even have to write it down. So what does it say? The maximum one should load on it. You can assign it the length of one times the length of the other.
Thank you for tonight.
Then we're on
Because over
track.
here the angle is 0 and the cosine is 0 minus 1. So I'll just write in parentheses the cosine of 0.
So what if they point in directly opposite directions? If one pair is that way and the other pair is that way, then what's the angle between them? 180 degrees. What is the cosine of 180 degrees? Negative 1. Now it comes to this. Why does it say negative 1? If they are perpendicular to each other, what is the cosine of 90 degrees?
And what is 0 times anything?
0, then the dot product equals 0, f, and only f. They are perpendicular to each other. And f and only f, it looks like this in mathematics. That's the symbol.
That's what it states clearly, and only that.
And then you tighten this one here.
Oh, so this isn't where I should be writing it. This is where I should write it. Kind of like a logic bulb.
So only if two vectors are perpendicular to each other will their scalar product be 0. The phrase this and only this could be cool if it was one of those short words someone came up with, like this is the thing. This and only this.
With 2 S's. That means this was just a this.
This is Peter plus this.
You're allowed to show off a bit, aren't you?
And one can prove that the way I defined dot products before. First coordinate times first coordinate plus second coordinate times second coordinate. This means that what is true can be proven by looking at a triangle and using the laws of cosinus. Now, I hope you all have a better understanding of what the dot product is. The dot product is a measure of how much two vectors assist each other. And by assistance, I mean pointing in the same direction. So it's a measure of how the two vectors are oriented relative to each other. And that can be used in physics, for example, for physical work.
But now I promise not to turn this into a physics lecture.
Because not everyone is as fond of physics as some might be. So that was board 11. And how much time do we actually have until 3:40 p.m.? Let's continue. What we're moving on to now is also really important to grasp, especially for the mechanics folks. It's the cross product because it can be used to understand moments.
Let's do that.
Let's just review the cross product as well, and the biotechs should just lean back and think that they might even need to use it. So on to slide 12.
I feel it too. The weekend is just around the corner.
Carbon product. Cross product can also be called vector product. So I should rather write either the same vector product or the same as the cross product. And what is that? You can't multiply vectors.
Forget it, but you can mint them, or you can cross them.
You can multiply complex numbers, but you can't multiply vectors. A cross product looks like this. Here is a vector.
You can cross it with another vector.
But there is a condition for you to cross them. They both must be three-dimensional. You can't cross two-dimensional vectors. So you can cross both A and B. They must be three-dimensional. You can create something akin to a cross product in 2 dimensions, which is called the determinant. But it's not exactly a cross product. It's related to that. So what is a cross B? It's a vector. When you cross A with B, you get a new vector. Now you know. Vector A crossed with vector B gives a new vector.
And the new vector is neither equal to A nor B.
It's also worth noting that AB prime is equal to AA prime. And AB prime is not equal to BA prime.
So that's a new vector, that one. You might be tempted to think that whether I say A prime B or B prime A doesn't matter. It usually doesn't. 2 times 3 is 6, and 3 times 2 is also 6. So when we multiply, it's definitely irrelevant. Or does it always not matter when we multiply numbers? Does it matter when we add numbers together? 2 plus 3, that's 5. 3 plus 2, that's also 5. It seems like it doesn't matter, but you must be extraordinarily careful in mathematics. Actually, I would say that one of the coolest things I've learned in math is to be careful with assumptions and intuition. Because I would think that when 2 plus 3 equals 5, I would say that if 2 plus 3 is the same as 3 plus 2, then I'd think that I've grasped the concept that order doesn't matter when you're adding numbers.
It's always true.
When there are infinitely many numbers being added together, then the order does matter. How weird is that, huh? It's so bizarre that everyone would think that can't be right, they must have calculated it wrong. But it can be proven when you have what are called conditionally convergent series. This means they can converge if you add them in one order and diverge if added in another. So when infinity is involved, you have to be extraordinarily cautious with intuition. It can indeed lead you astray. And that's what I mean by mathematics being the discipline among all disciplines that has taught me the most about being careful. Be careful with being overconfident because you can quickly find out that you're wrong. And mathematicians are always great at prompting you to figure it out for yourself. Then you end up realizing, oh shoot, you were wrong. So over here, you can easily get it wrong if you think that AB is the same as BA, because it's not.
So let's start writing this down. Across B
Is not the same as, okay, keep it steady.
And now it's rare for those who teach math to want to stand and talk about all the things that aren't correct. So should I keep writing endlessly on the board about everything that's incorrect? Because most of it isn't correct, right? But here is one of the things we bother to write down because it's what people think might be correct but isn't. That's why I've written it here. So now that we've discovered this, we better write down something that's correct, because it is true that the times B is exactly the same as negative B times A. So if you switch the order, it just changes the sign. That is the direction. Because as we've just learned, if you multiply by a weight that is -1, it rotates exactly 180 degrees without changing its length. Do you remember when we talk about scaling?
So this applies, I can draw a box around it.
So what have we learned about the cross product so far? A cross product between 2 vectors is a new vector.
It matters which way you cross them.
And you can only cross 3-dimensional vectors. That's what we've learned so far. What can I say about this new vector? Yes, the new vector is perpendicular to both A and B. So this right here is a vector that there is one vector, even though it has 2 vector lines. It's just one vector. And this single vector right here, it is perpendicular to vector A. And this vector 2 is perpendicular.
It's also perpendicular to B.
Well then, that must mean I can draw it. I can at least give it a try. So imagine now that you have a plane, and it's called a plane, not a plan.
Video is playing.
So oddly enough, a sheet of paper like this is called a plan in a library, a mathematical plane. I thought for many years it was called a plan. But it was actually on plan when we looked into one of the language councils. Imagine in this plane, there's a vector up here. And I've tried to draw it so that you can see it lies within the plane. Can you see it? This arrow, which should start and finish off the arrow, follows a line that's parallel to the edges of the plane to make it look truly three-dimensional. And here's another vector that also lies within the plane. It might be situated right here.
It also covers down the plan. And if now I call this vector vector A,
and I can draw this vector from vector B right here.
ACB.
Yes, I can do that. You take your right hand and then you use the 4 fingers that aren't thumbs. If you have 10 thumbs, then you've got a problem. But if you take the 4 fingers that don't look like thumbs and you let them rotate from A towards B down on the plane like this, so your thumb will point in the direction of the cross product, and that's called the right hand rule. So you use your right hand. It must not be the left one. That's why it's called the right hand rule, because you have to remember to use your right hand. And then there's another problem if you don't know which hand is the right one. But the hand that is the right hand is the one where the thumb points to the left. That's one way you can remember it. It's circular referencing. You have to be careful with that too. One should never argue for the truth value with the concept itself. So it doesn't mean anything. Then something's wrong this year. Everything in the Bible is true, because the Bible itself says that everything in the Bible is true. Yeah, that's circular reasoning. We can't do that in mathematics. Take your right hand and extend the 4 fingers that aren't the thumb. Then sweep them from the first vector towards the second one. Your thumb will then point in the direction of the cross product. That means I should draw a vector going up like this. And that's the cross product. And there should be a 90-degree angle here if you measure with a protractor. And there should be a 90-degree angle here too if you measure with a protractor. And this picture, you need to see it in 3D like this. So you take your right hand and then you let the 4 fingers that aren't the thumbs rotate from the first vector that I mentioned to the next vector that I mentioned. Now your thumb points in the direction of the cross product. So this here, this is A cross B, and A comes before B because I started with A and rotated towards B with my 4 fingers. And if I'm bold enough to do it on the table, then here you have vector A, where you have vector B. Do it like this. So that's A, that's B. So it stands up right here. It makes sense, and for example, you can use this if I still have it to show it. So here's weight A, and here's weight B. So there's a check mark on the dot. If it's vector A and it's vector B, and you cross A with B, use your right hand. So the way it works is you start at A and then rotate towards B with your 4 fingers, as if you're setting your thumb free, and then it goes in that direction. It's called the right hand rule, and if you are asked about it in an exam, you should be able to answer, even if it gets confusing at first.
What is it, Christian?
What does the Christian mean? Okay,
Yes.
and we've just seen that if I cross A with B, it results in negative D from here, if I cross B with A. So if I take this vector and position it here on my
Turn it
drawing,
180 degrees, then it'll be pointing downwards, you know.
so it's laid out here on my drawing.
And that's not A times B. This is B times A.
Because this is the same weight as if you took that one and multiplied it by -1. So what have we learned now about the cross product? The cross product is a new vector. It's perpendicular to both of the vectors we're crossing. And it stands perpendicular in a specific way, defined by the right-hand rule. So that's what we've learned so far. The last thing we need to learn is how long is it. So the mathematician is actually satisfied, but the physicist is not happy at all. He still hasn't grasped a bit of cross products.
But he's sharp with math now because he can figure it out.
How long is it from here to there? That's what we need to explain mathematically next. After that, we'll interpret it physically so we can understand what it means when we use it. In fact, it's not a measure of how much two vectors help each other. It's a measure of how perpendicular they are to one another when it's a coarse product. A measure of how close they are to being waffled.
So the distance from here to there.
It's the length of the cross products. You write it like this, you know. It's the length of the cross product vector, which we'll get to now. And there's a very good reason why it's been defined this way, the length of the cross product vector. Obviously, it's precisely as long as if you crossed them in the opposite order, because that's what changes the direction.
Just like saying the length of this one now. The link is right here.
That's not it.
The same vector as that one, but they have the same length. Because if I switch the order, then the sign would change, wouldn't it?
But changing the sign of a vector, it only rotates it. It doesn't change its length. So it's true that the length of that vector is the same as the length of the vector, even though it's not the same vector inside.
So how long is it then? A cross mark on that one?
Yeah, they decided to make it this long here.
How long the one end is?
Multiply by the length of the other, whatever that may be. Multiply by the sine of the angle between them. And that angle between the bonfire, it's on my drawing here inside. So V is right here.
Well, then we can already think. What's the biggest sinus curve?
It's 1. And when does sine equal 1? What should the angle be? 90 degrees. So the cross product can never be longer than it is when the two vectors are at a degree to each other. So the coarse product lasts as long as possible. The two vectors down here form a parallelogram. If you look at this plane from above, it could look something like this if I draw it to the right. Now I'm looking straight down at my plane and vector of this arch. That was vector A.
And put the weight back then, sort of like that.
And can you see that vectors A and B, they span?
A few little farms lay here.
So do you get that if vector A and B point in the same direction, then it's a parallelogram squashed together, resulting in an area of 0. Large vectors pointing in the same direction span a parallelogram that's just a line, and the area of this line is 0. And if the vectors point in different directions, so the parallelogram flattens out and becomes a parallelogram that's just a line with an area of 0. So the largest area is achieved when the two vectors are perpendicular to each other. Are you all following? And that occurs here when the sine of the angle equals 1, because the sine of 90 degrees is 1. So a cross product can never be longer than the length of one corridor and the length of the other corridor. Are you up for it? So the maximum length of a cross product can be, it's the length of one times the length of the other. It can't ever be bigger than that. So if one is 3 long and the other is 5 long, then the cross product vector can't be more than 15 long. Now there's something new you all need to get used to. If the length of one vector is in millimeters and the length of the other vector is also in millimeters, then this one is a certain number of meters long. It is a certain number of meters long. Each cross product is also a certain number of meters in length. It's certainly a number of square meters long.
It really boggles your mind the first time you hear it.
The length of the vector doesn't have to be measured in meters. If it's a torque vector, then it's measured in Newton meters.
It got torn up. Convert the measurements to meters, then the cross products will be in Newton meters. So you need to multiply the two units together.
When I first heard it, I was like, what? Can a length be measured in something other than meters? Yes, the length of a vector can also be measured in Tesla. That's magnetic field strength. Or in amperes, which is a current strength. Or in Newton per coulomb, which is electrical field strength. So a vector's length can be measured in all sorts of things. Depending on whether you're a bioengineer, a machinist, or a physicist, you'll need to get used to that. And if both of the vectors you're crossing with each other are measured in meters, then the cross product between them will be measured in square meters. Because do you know what this is, what it says here? These are areas, and they're parallelograms, they span out, measured in square meters. One side length times the other side length times the sine of the angle between them gives the area of the parallelogram, and we're going to look at that on the next board. So let's take a look at it right over here. Now we'll take the scraper. We just saw that LinkedIn is a cross product. Match the length of one vector, multiply the length of the second vector. Multiply the sine of the angle between them, which I'll call V for angle. And that's, congratulations. If this rate here is one vector, it is important.
So what should we say?
B,
And this right here is the second vector.
vector A. And I'm looking right into the plane that A and B span. It said that two vectors that aren't parallel span a plane. This means that if you imagine this to be a piece of wire and this another, and then I take an extra little piece of wire and place it here, and then put the whole thing into a wash tub with soapy water and lift it. Then the film that forms, that's the plane. It's a part of the plane they span because a plane is infinitely large. But two vectors, if they aren't parallel, they span a plane. And I'm looking at an angle onto the plane on this drawing. Do you get that these two vectors form a parallelogram, the area of which I'm about to write down? And there's an electrical basement here, A, and a small p, because that's the area of a parallelogram. Are you also on board with if you just had a drinking spree and you had to figure out the area? It's just length times width. That's how you find the area of a rectangle. Isn't that right? So what if you need to find the area of a parallelogram? So it's still just length times width. Why? Because imagine that I just draw a rectangle here. If I take this side times that side, what do I get? This rectangle right here. Can you see that if I do it, so I calculate something assuming that I didn't have,
But on the flip side, I miss out just as much.
do you see it? So the area of a parallelogram is exactly the same as the area of the corresponding rectangle, which is just height times length. So if I just draw the height here and call it h, then I can write down for you what the area of the parallelogram is. It's just h times the length of vector b. Are you following? It's h times the length of vector b. So sin of v is equal to h divided by the length of vector A. So it has to be the length of the vector because there has to be a side length. Well, then I can find h. I can find an expression for h just by multiplying that one over there on the other side, and then I found h. So now I can find the height. It must be the length of vector A times the sine of the angle. There are too many complications with this. And this you can now place in the hospital area there. What does it say? The area of the parallelogram is an email. The length of vector A times the length of vector B.
Gang sinus dB.
The length of vector A times the length of vector B And teams, the scene of the angle VH, that's exactly the length of the cross product.
That's how it has been defined.
So they were quite clever when they defined the length of the cross product vector, making sure its length was exactly the same as the area of the parallelogram spanned by the two vectors. And it's a pretty clever way to define the cross product, because then you can use it to find areas. You can also use it for all sorts of other things. You can use it to calculate the forces on charges in magnetic fields and stuff like that. But I hope that you
We
can
can see that the areas of this parallelogram here,
that's the length times the scene. That is the angle. And that's exactly what I've written here. And that's exactly how I defined the length of the cross product vector.
Now I can tell by your faces that we need to take a break.
All right, let's take our final break for today. And then I'll wrap up by giving a physicist's interpretation of the cross product.
It's finally the weekend.
Well, are you sure that you have a good idea? The last thing for today is the interpretation of the cross product. So what can we use this cross product for? Well, my first example is torque, so the mechanics folks might realize that's what it means. And my second example, that comes from electromagnetism.
Thanks for nothing. None of you have seen it before.
But first, the story of the moment. How does it relate to the cross product? The moment one should consider as almost like a rotating force, a tendency to make something rotate. So if I try to open the door over here, pulling on the handle, then when I pull with a force on the handle and there's a certain distance from where I pull to the hinge, you say that there's a moment trying to get the door to open. So the first thing you need to know about torque is that it's trying to get the door to open. It's a tough time. Torque is the moment of force. So simply put, if I have a hinge here, that's usually drawn like this if you're into mechanics, and here is a rod. This rod is the hinge here, and then there's a force here which I'll call F, and it's measured in newtons. So this force might be about 10 newtons. And I'm not even putting any vector arrows, because the only thing I've mentioned is the distance from here to there, and that's 10. Look at what? 10 newtons. So the length of a vector can indeed measure 10 newtons. And then there's a distance from here to there. That's the length of the rod. And I make sure that this angle right here is 90 degrees, so the force acts perpendicular to the rod. And let's say the rod is 5 meters long, so from here to there is 5 meters. 5 meters. If you take that force and multiply it by the length of the arm, you've got the torque around that point. So let's call that point A. The pivot point, so one would say that the torque at point A,
Just the power afterwards.
it's the force F. Multiply by this distance, which I could call R. So I need to say force times distance. I'm plugging in the numbers. That would mean I say 10 newtons. And then I multiply by 5 meters. And that means we've got a torque of 50 Newton meters. And that was the simplest example I could calculate, because here it takes place in 2 dimensions. And the force is perpendicular to the arm. So you just say force times arm. Job done. It couldn't be easier. So what does it correspond to if we use vector calculation? It corresponds to this being the length of the force vector, which is 10 units long. And this is the length of the r vector, which is the position vector to the point where the force is applied. And then there's an angle between them, which is 90 degrees, with a scene of 90 degrees. That's 1. So all you've got to say is 10 times 5 done, end of story. So that's the simplest example one can think of. So what if we now have an example where the force is at an angle to the arm? What do you do then? So here comes example 2. That was example 1, this one. Example 2. And then you'll say, as the examples get more and more complicated, that eventually I'll need to use a cross. In example 2, you might imagine that I have a hinge right here, where this point is called A. And here I have another arm. But now the force is oriented like this. So the force acts along this line here and then here. Now I need to find a place to measure the angle. Perhaps I'll measure the angle. So this is my force F, and it is still 10 Newton. The force's magnitude is the same as before, but it's just acting in a new direction. And it's still 5 meters. So we imagine the distance from here to there is still 5 meters.
So R is 5 meters.
What now? All right, now we can think that we need to find the effective distance from the line of action of the force. The line running through the force here, that's what we call the line of action of the force. If I were to draw it a bit more clearly, this line running through, that's the line of action of the force. You can either think, how far is it from the line of action to the point where I need to find the moment? And then you multiply it by the cancer. That's one way to do it. So you don't use the full 5 meters. You only use the distance that's right down here. So you're less than 5 meters. Because now you get a smaller moment. Since the force isn't perpendicular to the lever arm, the moment decreases. And you can see the more the force is applied like this, the smaller the moment becomes. Because if in the end the force is pointing directly in and the line of action goes right through, then there's no moment at all. And how does this relate to the door? It's like I'm trying to open a door, not by pushing like this, but by standing and pulling like this on the door. If I pull with the force where the line of action of the force goes through the hinge, then the door won't open. So the torque is 0. Can you see it? So one way to think about this is that I need to find that distance, and then I have to multiply it by the 10 Newton meters. Another way to think about it is that I only need to take the part of the force that is perpendicular. So you can split your force into 2 components, one here and one here. So if I just redraw that diagram a bit better to make it clearer, imagine here, RA.
And here's the arm.
And here I am, the force. And now I'm splitting my force into 2 components, one here and one here. Since this weight plus this weight equals that weight, you can forget all about F and replace it with this force and that force. Because these 2 forces together are another way to represent the force F. That's what you call breaking down a force into components. And now you can see that one component of the force lies along a line parallel to this arm here. So it doesn't create any torque at all. And this other one here stands perpendicular to the arm. Can you see that? There's a 90-degree angle between the arm and this direction right here. So another way to think about it is that you take that force component and multiply it by the full length. And it gives the same number as if you take the whole force and only multiply it with that length. So there are 2 ways to think about it. And now we have a third concept coming up, and that's the cross product.
And it always works in 3 dimensions too.
Happy New Year. All right, let's just go through this. So the headline is still the course.
Okay, it's got to be hush. Agreed.
So we could imagine that we now have a situation that looks like this. Here's the point where the hinge is. And this arm I'm describing with a vector, which I called the R vector. It's a position vector that starts at the point where I want to take a moment and ends out here where the force is acting. Let me just assign some coordinates to it so I can complete the calculation for you, and I'll just make up some numbers. Let's say that this is a 3-dimensional vector that extends a certain distance in the X direction, a bit upwards in the Y direction, and then it might extend a bit in the Z direction too. That's just not visible in my drawing. So this is a 3-dimensional vector we're dealing with. Let's say it extends 3 meters. Move up 2 meters. That's where I need to write a 3. So I'm looking at X, Y, Z, and then it goes out of the board. So I'm using a right-hand coordinate system with X, Y, and Z. So this axis comes out of the board, and then it extends 1 unit out. This means that the vector I've drawn here stands like this. It's positioned like this on the plane of the board, just tipped out from the plane of the board. So there's 1 from the tip and 1 to the board. That's why there's a 1 there. Right here at this point, a cancer is now at work. Let's see, imagine it looks like this. And that's the force vector F. And it also needs some coordinates. So now I'm inventing a force vector. It's called then.
Let's see.
That's 5 Newton meters in that direction.
What's up?
So we have 2 Newton meters downwards, which means a minus for going downwards. And let's say it goes into the board. So that's minus 1 Newton meter into the board. And now we're asking how large a torque does this force generate in space around that point if the arm is also in space. And that's not particularly easy to calculate. But that can be done directly with the cross product. So let me first tell you about how the cross product can be used to describe a moment. So imagine this as a hinge point right there. And this is an arm hinged here, swinging like this. And this right here is a force. If there's a force acting in that direction around this arm here, you get it, right? It will try to rotate it like this. If there's a force pulling that way on this arm here, which is hinged right here, then that force will try to rotate it like this. And what do I get if I take that vector and cross it with this one? So I should say this vector, and with the right hand, this vector crossed with that vector gives me that vector. So I get a cross product vector that stands up like this. How can that correspond to a moment? Well, you take your right hand and wrap it around the vector so that these 4 fingers are wrapping around the vector. And now your thumb will point upward in the direction of the vector, and the 4 fingers will indicate the direction of the moment. That's how a vector can be used to describe a moment. So that one crosses this one, gives that one, and the vector that stands up, that's a moment vector. When you take your right hand and let the thumb point in the direction of the vector, the other 4 fingers, which aren't the thumb, will point in the direction of the moment.
Can you imagine that?
So I need to say R vector crossed with F. I should not say F crossed with R. That way I get the wrong direction. So you just got to sit and mull it over a bit. But the torque here as the force acts around the point A, I can find by saying R vector.
Crossed with the F vector.
And then let's just get started.
Yes,
So
we have substitute 3 over 2.
And yeah, pay attention. What's the goal with this?
And it's a place.
And that was our day. Newton on that force. And once you've looked at this example, you'll see why examples aren't always given in mathematics. It's because the math only gets more complicated when you provide examples for physics. But for some, it suddenly clicks, what am I actually doing? So let's finish this up. I need to take this vector called R. It's 3, 2, 1. And I have to cross it with the vector called 5, -2, -1. And now, here comes a neat trick. This vector goes 3 in the x direction.
It's a deal.
Yeah. And 1 in the z direction. So this vector can be written like this. 3 times the unit vector I plus 2 times the unit vector j plus 1 times the unit vector k. This is another way to express vector r. So this is vector r in disguise. And that I have to cross, but it moves 5 newtons in the x direction, then 2 newtons in a negative y direction, and 1 newton in a negative z direction. So it's called 5 times the unit vector I, minus 2 times the unit vector j, and minus 1 times the unit vector k.
And now we just need to cross-check it, and then the answer will come out.
All right, now watch how you do this. You have to say the cross product positive, the cross product positive, plus the cross, plus the cross, plus the cross, plus the cross. You gotta know how to do this. So I'll explain it over here first before we get to it. And this is board 15. No, it's still 14. I just hadn't finished it yet. So to get to it, let's draw that 3D coordinate system again here. This right here is the x-axis where the unit vector I is located. And this right here is the y-axis with the unit vector j positioned on it. And this right here is the z-axis, and that's where unit vector k is located. So they came up with this clever little thing where if you say I cross j, you get k. Just try using your right hand to do it. You should move from I to j. So your thumb will point in the last direction, which is the cross product. So I crossed with J yields K. What if I say I had cross K? Ud times K equals E. I'm marking J with an X, and then I'm passing it on. And short crossed with an I.
It makes sense.
And intersected with I.
Do you guys think I have them?
And we know from when I defined it that if I swap the order, what happens then? The sign changes. So let's jot down, if I say J times I, then I get minus K.
And if I say K times J,
then I get I.
and if I say I times K,
So I get minus J, and the last thing you should know is that if you cross a vector with itself, you get the zero vector. Why do we do that? Well, a vector, no matter how large a parallelogram, it spans with itself. Zero area of J's parallelogram. Another way to say this is how large is the angle between a vector I and the vector I itself? 0 degrees. What's the sign of 0? 0. How long is it then? 0. So what kind of vector is it? The zero vector.
so in X in
Here is
Cool.
0.
dagen.
J, I am the zero vector.
And finally, K cross K results in the zero vector. And now we have all the ingredients we need to calculate this down here. So let's do that. Multiply this by this, and there's an I times I, which equals 0. And I've just moved on, in case you need to move to the side because of a 2, right? But this times that, or this cross that, results in the zero vector, because it's an I and an I. So now we can skip that. Away with it. Then there's this and that. 3 times negative 2, that's negative 6. And then there was an I cross J, and I cross J. What did that give? It gave a K.
So I'll just write a K after it.
So now I've taken this and that one and this one. Next I need to take this and that. It says 3x minus 1. That gives minus 3. And then I multiply it by K, and I by K, what does that give me? That gives negative J. Do you see that? Negative J. But a negative times a negative, that's a positive. So I need to remember to write the sign. You should always keep your tongue straight in your mouth when doing that. So now I've taken that cross term and that one and that one. Next, I'll take this cross term. 2 times 5, that's 10. First, I'll write down 10. I don't know the sign yet. But it gives 10. And J cross I, that gives minus K, so it should be minus. I'm taking this one and that one. Oops, there's a J and another J, so that results in an imbalance. So that was easy. Then I take this one and that one.
It give her minus 2.
I can go ahead and write minus 2, because a minus can easily be turned into a plus. So that gives me minus 2. And J cross K, where did we have that? It gave I. So no need to change it, just have to write I. So finally, I'm missing this one, this one, this one, this one, and this one. And this one with this one, that makes 1 times 5, which is 5.
And kiss it.
That's what makes it all worthwhile. So I take this one and that one. That gives us negative 2. So there's K cross J, and K cross J gives us negative I. So it turns into a plus, and then it becomes the I vector. And in the end, there's K times K, which gives us the zero vector. So we have the answer. Now we just need to collect everything together. Okay, let's see. What do we have with I? We have negative 2y plus 2y, which cancels out. How much do we have with J? There we have 3J and 5J. That must be 8J.
And finally,
So I have something with K. I have negative 6K minus 10K. That's negative 16K. So this is the answer. And this can be written as a vector with 0 in the x direction, 8 in the y direction, and negative 16 in the z direction. And that right there, that's the torque. So it's measured in Newton meters. How strong is this torque? How many Newton meters is it? It's 8 strong in the y direction, and it's 16 strong in the negative z direction. If you just want to know how strong it is, then you find the length of this vector. That will give you the strength of the torque, meaning the square root is 0 squared plus 8 squared.
negative 16, the whole detail.
And then you get the moment. And just like that, you can see that cross products can be used to calculate moments, for instance. But it's not certain that the theory has become any easier because we've taken an example, but maybe.
Have a great weekend.
Thanks for that.